Magnets look simple at first glance, but their behavior hides a deeper mystery. No matter how big or small they are, every magnet always has a north pole and a south pole. You can cut it in half, into quarters, or grind it into tiny fragments, and every piece will still form both poles again. This raises the obvious question: why can't we isolate just one magnetic pole? The answer begins with the internal structure of magnetic materials. Inside a magnet are countless tiny regions called magnetic domains. Each domain behaves like a microscopic bar magnet with its own north and south poles. When these domains point in random directions, their fields cancel out, and the overall material shows little or no magnetism. A magnet becomes strong when many domains turn and align in the same direction. Instead of pointing everywhere, they begin to line up, reinforcing each other's magnetic fields. The more domains that align, the stronger the magnet becomes. This alignment also creates the unmistakable north-south pattern we see in every permanent magnet. Now imagine cutting a magnet in half. The domains inside each piece do not vanish or lose their structure. Instead, they adjust to the new boundaries and form fresh poles at the cut surfaces. What used to be the middle of the magnet instantly becomes a new north or south pole. This is why breaking a magnet never produces a single isolated pole. For a true one-pole magnet to exist, the internal structure of the domains would need to be fundamentally different. But magnetic domains are linked to the behavior of electrons inside atoms. Their magnetic effects come from electron spin and motion, which always produce paired poles. The physics simply does not allow one side without the other. It helps to compare magnetism to electric charge. Electric charges can exist independently as positive or negative. You can isolate one without the other. But magnetic poles are not separate particles. They are part of one continuous magnetic field. So separating a north from a south is like trying to cut a ripple out of water. In classical physics, the magnetic field around any magnet forms a closed loop. Field lines leave the North Pole, curve through space, and enter again at the South Pole. These loops cannot start or end in empty space, because the field must stay unbroken. The two poles remain permanently linked. Maxwell's equations formalize this idea mathematically. One of these equations states that there are no magnetic monopoles in nature. If a monopole existed, the entire framework of electromagnetism would need to be rewritten. So far, every experiment ever performed has supported the idea that magnetic fields always form closed loops. Scientists have searched for magnetic monopoles for decades. Some theories predict they might appear in extreme conditions, such as inside cosmic rays or during energetic particle collisions. However, none have ever been observed. If a single monopole were found, it would be one of the biggest discoveries in modern physics. On the atomic scale, magnetism is governed by quantum mechanics. Electrons have a property called spin, which gives them tiny magnetic moments. When enough of these moments align within a material, they create the dipole pattern we recognize in everyday magnets. This quantum structure naturally favors pairs of poles. Even advanced materials such as superconductors or exotic quantum systems cannot truly isolate a single pole. They can twist magnetic fields into unusual shapes, but the dipole structure always returns. This shows that two poles are not just a feature of ordinary magnets, they are a fundamental rule of magnetic behavior. So the hidden reason magnets always have two poles is rooted in the laws of physics themselves. Electrons, magnetic fields, and the structure of matter all force magnetism to appear in pairs. Until a magnetic monopole is discovered, every magnet, no matter how small, will always recreate both a north pole and a south pole. That's it for today's video. If you enjoyed exploring with me, don't forget to subscribe to Science Lab, where we turn everyday things into scientific discoveries. See you next time.